presenters actually we planned four, but now we have three because one of them is she is ill, so she couldn't able to attend this online meeting. But we have our topic is reinforcement learning. It's a kind of machine learning technique, and we have three experts on that field. I want to say Dr. Pankaj Dadheech and Professor Dr. Varalatchoumy and Dr. Neha Janu. They will present the reinforcement learning, and our first presenter is the Professor Dr. Varalatchoumy, the learning process of reinforcement learning. So Dr. Varalatchoumy is she is the head of department of this CHOS in Bangalore, Cambridge Institute of Technology in Bangalore. She is academician with 18 years of teaching experience and 8 years of experience as a researcher. She had completed her bachelor and master of technology in computer science and engineering, and she had pursued her research in the medical image processing under the Visvesvaraya Technological University in Karnataka, and has done major contribution toward detection of malignant tumors at a very early stage. She has more than 30 international journal publications, 15 patents. Is very excellent, and many awards like Excellent Paper Award, Academic Excellence Award, and Distinguished Educator Award. So it's very successful and very high contribution in this field, especially in the artificial intelligence and in many machine learning. She is very good. So you can share your screen, Doctor.
Yes, Mr.
Yeah. Okay. The screen is yours.
Yeah. Thank you, Mr. Imran. Thanks for the introduction. So I just share my screen, the presentation. Yeah, so hope the screen is visible. So is the screen visible,
Yeah.
sir?
Can the screen is okay. Okay.
Yeah, okay, thank you. So good afternoon, one and all. So first and foremost, thanks to Christian sir and team for the opportunity to give a presentation on reinforcement learning. So as we all know, to kickstart with machine learning, there are basically three types of learning under machine learning. One is supervised, next is unsupervised, and third one goes with reinforcement learning. So today I planned the presentation in a way like I introduce what is reinforcement learning. Thereafter, the basic terminologies related to reinforcement learning to have a good understanding of the topics. And I've touched upon three algorithms, like the algorithms which are used pretty much nowadays to develop several models based on reinforcement learning. So those algorithms are focused, and three case studies, like three projects, gaming projects has been developed using the reinforcement learning. So those projects also I'll be presenting. I've tried to explain about the coding also and try my level best to give the maximum explanation. But I've added everything in this slide. If needed, I can also share the material. Fine. So let's kickstart with. So when it comes to reinforcement learning, as we all know, it's an very important area under artificial intelligence. So a best way wherein we can make a model literally think like a human, but a more best approach, like why reinforcement learning literally kickstarted or why people started using reinforcement learning more was it was very much practical and apt to be used in all real life gaming application, specifically for gaming. So there is no hard and fast rule like sorry, there is no hard and fast rule like it has to be used only for gaming application, but it sees a very best implementation, or rather it can be used very well when it comes to the gaming application. The reason being it learns more with respect to the real-time data. It learns a lot from the real-time data, and it doesn't expect all the data to be fed in the very beginning itself. That is another major advantage. And the third thing is like it can handle missing data, or some new learning has to happen. That goes very well with reinforcement learning. New learning in the sense, the learning which was not even fit. Learning in the sense, again here, the basic idea. Even, for example, let me take a best example of a chess game. So reinforcement learning, it works out very well when it comes to developing a model which can play a chess game. Any game for that sake. But again, why I'm more attracted towards a chess game, there is a reason. When it comes to the chess moves, as we all know, there is something called as the basic rules and regulations of the game, which has to be fed obviously to the model. At least the basic moves, each and every coin, how it has to move, how the changes has to be made, the basic things has to be fed. We'll be calling that as a policy very soon. I'll be touching upon the topic. So though we have all the basic moves kept, and maximum, we can tell what might be the best possible moves in order to win the opponent. But as we all know, when we start playing chess, how the opponent thinks, what are the different ways they would think, again based on their expertise and their experience of having played the game several times. Obviously, they will be more quicker in deciding the moves, and taking a call upon the best moves. So it is, if suppose we try to create a database for say, okay, for all possible moves in a chess game, it's next to impossible. As we all know, it's next to impossible. So it keeps on changing, and it's almost like the model or the agent has to learn it over a period of time. So that is the best in reinforcement learning. It doesn't expect that complete learning process to be spoon-fed totally in the beginning. So it literally learns as it keeps on playing the game time and again. It keeps updating its database as well as learns and becomes the expert at one point of time, obviously in winning the game. So this is somewhat, the most best thing related to reinforcement learning. So initially, when reinforcement learning started, it was more oriented towards manufacturing fields, and to solve control system problems and all stuff. But later they got to know it's not like it can be used only over there, but pretty much in several applications. Like nowadays, again, it's not restricted only to gaming applications also. I think another speaker will be handing upon the applications part. That time we will get to know more. So it's like several application nowadays. Everywhere, if you see, we can see the implementation of reinforcement learning going on well. So, as I was mentioning just now, like reinforcement learning, it's nowadays like AI is working, or AI works with reinforcement learning. But when we go with reinforcement learning, what was the starting point? Where it all started? Like what, or I want to put it other way around also. If we have to understand reinforcement learning in a more better way, our prerequisite would be deep learning. So we should have some idea about deep learning, or our basic neural network architectures and stuff, how it works. So be it the ReLU of the deep DNA model or our TensorFlow, all this literally it led to the advancement of our reinforcement learning. So it all kickstarted with deep learning. So how once we started playing, once the researchers and scientists started playing with deep learning, they started getting to develop. They were able to develop more better approaches to solve a problem, and gradually it came up. So that is how the reinforcement learning took its form. And next important thing is, this is quite different from our supervised and unsupervised, as I was mentioning from the beginning. Very different. The reason being, when it comes, I just come back to this slide. When it comes to the reinforcement learning, I just want to talk more about the images over here to explain how it is different from supervised and unsupervised. So as we all know, when we develop a model, okay, when we are trying to train a model, here I want to make it very simple. It can be as simple as you're trying to train a toddler. So toddler is totally new to anything which is being taught, or anything whatever the toddler sees in and around. So when we are trying to train a toddler, it so happens there are basically two ways of training. One is, for example, I just show a particular object, When I'm introducing object itself, I name the object. As we all know, it is very simple. It's called supervised learning. I give a name for that particular object. If I'm going to show a bicycle, whenever I'm introducing, might be even for the very first time to the toddler, I introduce a bicycle as a bicycle only. I name it and do. So that's why it's called it's supervised. Already the label is being given, and whenever the person sees it, it gets registered as bicycle in the mind. Unsupervised, we tell these are all the features, this is how this particular object will look, but we never go for giving the name. We allow the model or the mission to figure out what it might be. So we don't give the label finally. We don't tell. These are the characteristics, but we don't, for example, we don't tell the name as water, or we don't tell the name as a fire or something. We just allow the system to learn. When it comes to reinforcement learning, it's slightly more better and beautiful approach wherein it's not like trying to detect the objects or something, but we are allowing the model to literally carry out some actions. It performs some actions and it learns through its own actions. But again, it's not like the model is going to have a database already telling this is correct, this is wrong. Based on what action the model does, we actually name it as agent. Whichever model or whichever mission or something which is going to carry out the action is going to be called as an agent. Now, based on the action which is carried out by the agent, we are going to give some rewards similar to a toddler. When a toddler does some predictions properly, just again, I always correlate this to my students also. We have to just put ourselves into the shoes of a toddler and think, just let's imagine. When we were very small, right? It so happened when people introduced the same bus or a bicycle, for example, I just started thinking other way around. Now, when a bicycle, I'm introducing it to a kid, unfortunately, what happens? First, I might show an image of a bicycle. Then I might show that bicycle on a television, or a movie or something. Realistically, the bicycle can be entirely different. So, as all of us know, we don't have one single bicycle which is going to be flying all around. It's so many varieties of bicycle, and so the same bicycle will be seen by a toddler in different sizes also. But to what extent we train is, though we show a 3D model or a 2D model of that particular object, but finally we train it to the extent wherein, in whichever form the toddler sees it, the toddler has to call it as a bicycle. Amazing. So the same thing happens over here, but in a slightly different way. So again, sorry, getting back to the same example, how do we appreciate the toddler? How do we tell whether the toddler recognizes that bicycle as a bicycle? We try to give some motivating words. We appreciate. That appreciation is nothing but a reward. We literally appreciate them. Or when it goes wrong, there are different ways of handling it. Some people motivate, some people tell it's totally wrong, and it goes to the extent of giving some punishments also at times. So it varies from person to person. So basically in reinforcement learning also the same thing happens. So we can just visualize our model as an agent. So this model is going to perform some action. Okay, it's literally going to perform some action. For say, with the image in hand, we can visualize like the model might literally go and touch that so-called object of fire, or it might touch the water. So when the agent goes towards the water, there is no problem at all. But when it goes to the fire, we know what happens next. That's quite dangerous. So in this case, what we try to do is that action, based on the action, we are going to give some rewards. And this reward is something which is going to give some confidence to that agent. It is going to tell the agent, yes, next time also you can carry out this action. Not a problem at all. It has a positive reward over there. Like I give plus 50 points. To a toddler, I may give a cookie or some candy. So that is a sort of motivation and confidence mainly for the toddler as it can continue with it. So the same thing happens in reinforcement learning. So this is how it works. So basically in reinforcement learning, we have certain terminologies which are commonly used. One is called as an agent. So agent is something which is going to learn and do some action. And basically it is an agent who has to take the decision. This is something what we need to register very well. So when we tell a machine plays a particular game, it is basically the agent. So the next move is going to be decided by the agent, and there is not going to be there any human at the background at that very instant to take the call. So that's very important. And environment is nothing but the exact surrounding or the place where that agent is going to carry out some particular action. And by now, all of us would have understood. So actions are nothing but the various choices that can be taken up by the agent. So when it comes to playing the game of chess, okay, or any other game for that sake, the various moves are going to be the action. And related to this, we have one more terminology also, something called as a state table. So based on the actions which can be carried out, okay, every state after a move, how does my chessboard look? So that is something called as a board state. So for every move, all possible ways in which the board looks, that can be stored as a state space. So the agent gets more better idea. Okay, if I make this move, this is how it will look. But again, based on the opponent's move only, the next call has to be taken. So what happens, the agent will be backtracking in that particular state space and it will select the next move. And as I told, rewards is again part and parcel. So based on the feedback, a positive or a negative feedback, the agent can rework on choosing the next move over there. So what is the final goal of reinforcement learning? Finally, in this approach is actually it is not like only doing some particular action here, but our main aim is based on the number of times the agent is going to do some particular thing, its action database should go the best. So if suppose for say an agent has played a particular game around 10 times, the 10th time, maybe we can set a goal. So the 10th time, at any point of time, it shouldn't be in a position where it is going to lose that particular game. So as the time passes by, as the training increases, as the number of games increases, obviously the performance of the agent or the model has to go to a better extent. So this is our whole goal of reinforcement learning. So now let me come back to this slide. Why we had gone for reinforcement learning? Why people are more behind reinforcement learning? So obviously for several reasons. As I told in a short, as a gist, I told this in the very beginning. So first and foremost thing is when we move towards big data analytics. So obviously when it comes to big data analytics, currently there are several problems which are being faced. See, how we actually carry out big data analytics is we try to take samples of the data and we try to minimize the dimensions or the so-called feature set and stuff, and then we'll be utilizing the data. That is how it goes. So now what happens over here is since I'm trying to work on very minimal set of data, it gets very difficult for me when I have to maximize it. Suppose I have to literally take it out for a different dimensions of data and it goes very difficult. Might be my model might perform very differently also. Second thing is whatever input data we have collected, we don't know every time whether the data is available for us, missing data. And third thing is, what is the guarantee that the data is correct, the reliability of that data? If I get some unwanted value, usually called as a noise, so how will my model react to it? So basically, reinforcement learning helps me to literally carry out the work with a very minimal data in the beginning. As I told, it learns all over and it can work very well for any new data also. So these are all the positives when it comes to reinforcement learning. And easily it can adjust to new environments. It can relearn, okay, unlearn and go ahead. So all these are possible with our wonderful deep neural network algorithms and several other algorithms which we use to build the model. Yes, so I just mentioned this, and yeah, the same thing what I mentioned just now. So basically we have the agent which is going to work in a particular environment and it's going to apply some actions on an environment, and based on its action, it's either going to be given a positive approach or a positive reward or a negative thing. And based on the reward, one more parallel thing, what happens is, as I told, the policy is nothing but the collection of details, like what is the next state that agent can take. For say this example, so in the next move, whether that agent can go near that fire or not, or whether the agent has to move only towards the water. So the next state, that state table or the database update with the policy, basically we call that. So that policy update also will be happening based on the reward. And yes, so this is how the whole reinforcement learning works. So as I told, there are few terminologies which are related to reinforcement learning. When we know something about reinforcement learning, these are the very basics. We should be highly aware of it. So the first one is policy. Next one is called as a reward signal. Third important thing is a value function, and the fourth one is the model. So policy, as I kept mentioning till now, something which gives all the details to the agent about the various states. What is the next step it has to take? What is the next move it has to do? In which particular direction it has to move? Why it shouldn't do certain things? All this will be in the policy. So to put it in a very specific English term is a sort of rules and regulations which has to be adhered to. When it comes to the implementation part or data structure part, it can be visualized as a lookup table. So basically a lookup table and a function which is going to help us to retrieve the data from that lookup table and decide what is the next step my agent has to take. And again, one more important goal with respect to my policy is reinforcement learning is how to come out with the optimal policy. So here when I mention optimal policy, literally I'm focusing about a maximum robust model. I want to develop an agent which is going to literally minimize the error in carrying out the process. So a highly robust agent, to what extent we can create it is something going to be called as a optimal policy. So over a period of time, as my agent keeps on working, okay, on that particular environment and on several states, based on the learning, what happens, the policy keeps on getting updated. So obviously at a particular time, a particular point of time, we can expect the policy to be the most optimal policy with very minimal error and the best solutions given. Okay, and the reward, again, I have explained about all this just now. So reward is nothing but something which is really going to give a clarity to my agent. Whether I can consider this particular move or not. Is it considered to be positive or not? Can I update it in my policy or not? Or based on this move, whatever I've taken now, do I need to make some changes to my learning what happened previously? Same example of a chess game. So what happens when the agent is taking the next move? Because of that, it has lost, okay, a particular point. Then obviously, suppose there were around 10 moves which was made prior to that, the agent or the model has to rethink. Are those 10 moves fine? So where exactly have I gone wrong? Is it only in the previous move, or there was a series of move which has left me over here, almost like a backtracking approach? So literally it has to go back, update the policy or the database over there. And value function, yes, something which is going to help me to predict to what extent, if suppose the agent decides these are the moves which it has to take. Okay, it already decided some particular flow in the mind, and I mean that agent has some plan. So now what happens? The value function will be helping out to tell if suppose this particular set of moves are planned, what is a guarantee that we are going to land up in an appropriate result, like we will win that particular game. So sort of prediction, right, in every level that we are moving towards the positive goal over there. So that will be the value function. And finally the model here. Model, again, since I have used that agent and model interchangeably, kindly don't get confused. This particular terminology with model is nothing but that particular environment. Means there are two ways of developing the reinforcement learning. One is like we create that model, make the agent work in that model, then allow the agent to learn. But there is no hard and fast rule. For example, let's take this scenario, right? So this is a real life environment. Let's imagine or visualize. Typically, there is a robot which is allowed to move in an environment, real life, in a room where there is a water placed at one end and a fire placed at the other end. Just a typical environment. So are we going to simulate this environment by any chance and make the agent understand these would be the characteristics of the fire, that's why it shouldn't go there or what? So this sort of simulating the model and trying to create that environment is going to be called as that term model in reinforcement learning. But this machine, what we try to create, or that robot, okay, or some particular thing which is does that learning is going to be called as agent here. So as I told, these are the terms which we have to be aware of to begin with. And reinforcement theory, usually it goes like positive reinforcement, negative reinforcement, punishment, and extension. So these are the four things wherein all reinforcement learning and any approach we take will be fitting into any one of this. So when it comes to positive reinforcement, a total positive behavior, like everything goes well, everything goes well, it's completely positive rewards what the agent gets. So the agent keeps on doing everything correctly. Things are going fine, no problem at all. When it comes to negative reinforcement, based on the rewards, okay, the negative behavior of the agent minimizes, and obviously the positive behavior increases. So it's almost like over a period of time, the agent's performance is improving. When it comes to a punishment, when it goes to the extent of punishment, that means multiple times the agent is literally failing. It's not able to learn on its own. It's not able to update its policy appropriately. So typically it's failing multiple times. So gradually it's moving only into the negative direction, and obviously it will reach to the point of extinction. So extinction means what? Typically the agent fails. It tells like, I cannot take up this task anymore. It's completely lost. Okay, almost we close it. And many times what happens is, when the moment the agent goes with several punishment, it will reach to the point where literally we have to rework and start building that agent from the beginning. That complete learning from the beginning, it has to happen. Okay, so as I told, I've touched upon few reinforcement learning algorithm, and literally I'm giving only the basics over here. Like if I have to deep dive with the algorithm, it needs individual sessions. So I've taken up 3 algorithm. I've tried my level best to touch upon the important concepts related to the algorithm, as well as 1 project for each algorithm. Okay, so deep Q is the first algorithm what I've taken. So when it comes to deep neural network, it's similar to the deep neural network. Only thing is like, we'll be making use of a Q function. It's a specific function which will be helping us to understand whether based on the current state, we can go ahead with the next state or not, taking up the next move. Will it be helping me to reach to my goal? Okay, will I get more positive rewards or not? So this is something what will be happening over here. And this is how the Q function will look like. So S is basically the current state, and A determines the action. So when I'm in a particular state, what action I need to take so that I move to the next state with the goal in mind. So basically, if we see R here, the factor R, it is going to determine the reward. In the current state, when I apply certain thing, whether I'm in the positive direction or negative direction, whether I won it or lost it. So based on this reward, then I go for deciding, which is the next state I can make a move. So basically, decision of the next step I need to move will be based on my current state, and this current state will be decided by the previous state. So this is how the flow goes. And what I try to do is, always I try to concentrate upon the maximum value related to the difference between the state rewards. So if suppose the difference between, I mean, the reward is really in a positive direction, then it's understood I can take it up, I can choose the next state. So it comes almost like this. When we visualize a chess game, now, suppose I had an initial board state. For one particular move of a coin, there are multiple board states which are possible next. We can just visualize it as a tree. So one state is a root node, and you have all possible states of the boards that can be obtained based on the moves as a branches of the tree just coming down. Okay. So now out of these many states, which one I have to select? That is something I have to take a call now. So that path, thereafter in the path of the complete tree, I'll be able to reach my goal. So for this, what is one important thing is a alpha factor. So in every machine learning model, if you see, we have something called as a learning rate. That is something which will typically determine whether the model has achieved its goal or not, and what is the time at which it achieves, what is the maximum possible, best approach it has taken. So learning rate is multiple times we try to keep on training the model. So based on that number of training, number of epochs and parameter setting only, we can check out the model's performance also. It's typically test and trial approach when it comes to the learning rate. So this Q function, when it is used in a deep neural network, it's going to be called as our deep Q algorithm approach. So very simple and quite easy also. So we took a case study, like me and my set of students, we took a case study on developing a snake AI game. It's like very a simple game. Way back in certain small video games and all, you would have seen way back in 1990. Same game we have tried to develop here, wherein we want that particular this portion, this colored circle stuff. Now we can just imagine that to be like a snake or an object which is trying to move to get its food. That small red triangle is nothing but the food. So we want this particular snake model to keep moving around. This is the environment. This whole space is the environment. So I want this to just keep moving and literally get its food. But based on the condition, it shouldn't hit the boundaries, nor it has to self-loop. It shouldn't circle around itself. So this was completely developed using our deep Q algorithm over here. And when we try to develop the deep Q with respect to the GUI, what is displayed over here, right? So these particular circles were developed using the name tuple approach in Python, wherein every particular point, that location also will be recorded, right? And the food was just a small rectangle, but with the coordinates. So what is more important here is the location of that food in every place so that we can backtrack and build the policies appropriately. And yes, so this is how the whole thing went. So if you see, the agent here is nothing but that particular snake which keeps moving in order to catch the food. So once it is able to get the food without making any flaw, plus 10 points was given. And if suppose it has missed it, obviously a negative reward of minus 10 was set. And based on the Q function only, each and every action was decided. Next important thing is like several times the agent has to keep on repeating, right? We set the learning parameter in such a way it keeps repeating it, and at one point of time we were able to achieve continuous victory. I'll just show you. When I show the video, it will be more easy. And as we all know, that agent can move in 4 directions. One is upward direction, downward, left and right, in order to get the food. Okay, so as I told, I've just added few codes. Before getting into the code, I think once we can visualize a video how it works. Yes. So if you can see, initially there is a very quick movement and several times it is hitting the boundary. So it's all failures. It's not able to catch the food. That red is the food over there. First hit was that blue thing on the graph we can see. So that was the first hit for that snake. And gradually the training kept on increasing. Okay, more trainings are happening. Again, all these are based on deep Q approach. So as and when it fails, it is trying to update its policies. It's trying to update the parameters over there, fine tuning the values, where all it's a miss, why it goes to the boundary. So over a period of time, if we see, it's more hit, like it's able to catch the food. The errors are minimizing. Yes, so it's a very good approach over here. So over a period of time, it's increasing. But again, every time it won't be only a positive curve. So it's all the training what happens over here. So again, at some time as the size increases, that also happens over here. If you have observed, the size of that snake, okay, gradually we are increasing. Initially, we started with just three circles over there. So as the size increases, again, there will be a lot of problems which has to be taken up. So again, training has to change, parameters has to change. So this is how it goes. Okay. So now I'll just get back to the coding part. Just a quick glance of the coding. So it's very simple. First, we started with developing, the init function. Basically, the GUI has to be set. So this function was used for setting the GUI, the windows, and trying to create that snake stuff and everything. And when it comes to the reset function, basically trying to fix the which direction that snake has to start. For example, in the right direction, almost towards the center, it has to go down towards the center of the GUI screen and then start its work. Start the game. And the next important thing was with respect to the linear QNet class, that is basically the QNet model which has to be called over here. It uses a neural network model. So we feed in the input layer size, the hidden layer size, and the output layer size. All these are being passed as a parameter. And basically here in the linear QNet class, forward network is being used. Feed forward network will be used, and ReLU approach is being used as the activation function for the feed forward network. And the training step, as we all know, these are the basic things which has to be in any particular reinforcement learning algorithm approach, the current state of the environment, which is going to, as we keep on updating the state, our policies are going to get built at the back end. And then we have the action, what that agent has to do next. That will be determined by the action, and the rewards, the next state, all this we are going to just do it over here. So here we try to call upon with the parameter value, and we are going to tell how these settings can be done. Right, and basically TensorFlow is also part of it. Like we just call the tensor parameter to set the value, and the training I've just shown over here. So get action function, how it helps in trying to bring out the result over there, whether this action can be taken up or not. Next, what is the next step to be taken up will be determined by the get action function. Train function, train is usual. We start our training, okay, of that model, and then training and testing happens, and finally we decide upon the model over there, model's performance over there. And yes, so get action also I've explained. Basically in get action function we were trying to calculate the epsilon value. Here I want to highlight one important thing related to reinforcement learning. So when it comes to reinforcement learning, there are two things. One is exploration, another one is exploitation. So exploration is still now my agent has not come to a point like it knows this is exactly the steps I have to take in order to reach my goal. So it keeps on exploring, right? It keeps on exploring. The moment it gets to know, after several training, after several games and all, at one point it got an idea like, yes, it is perfect. If I follow this path, 100% I'll be leading to the goal. That is something called as exploitation. So the moment that clarity is set, the model starts following something called as exploitation. So higher the sort of means the value of the epsilon, it's understood like the more clear the agent is. So once it is gone to exploitation, there is one single drawback with exploitation. The almost the agent stops learning to some extent. It doesn't update its policies very much. So, but always this is a trade-off. If suppose you want to keep on exploring more, reaching the exploitation takes more time. The moment you decide this is more than sufficient, this learning is done, you can move to exploitation, exploring will stop. That agent will stop doing that learning. So this is one important concept in reinforcement learning again. Okay, so several things I've added. I think due to time constraint, I will just move quickly. So the place step and again the policies, how the next action can be added, everything I've explained over here. Just now I showed the demonstration. Okay, so the next algorithm is NEAT algorithm. Neuroevolution of augmenting topologies algorithm. This basically came with the concept of genetics, biology. So it so happened when they started using deep neural network and all the neural network model, at one point of time, so as we know, as we all know, this is how neural network will work. We have a specific node, we give the input and we have the output. The deep neural network, we have the input layer, hidden layer, and of course we have an activation function for all the nodes. So when it comes to the feed forward approach, we know again there is something called as bias and weights linked to it. We are going to analyze the performance, we are going to check the output, and accordingly we are going to change the values, the parameter value, so that we get a better result. Now what happened, what was the drawback with feed forward approaches? Like it so happened like getting that appropriate result, okay, is always not guaranteed, and there were certain drawbacks which were faced, which they thought it could be overcome by the concept called as genetic algorithm. So genome. So if you ask me, I would typically tell, when we talk in neural network, every particular neuron over there, okay, the node can be called as a perceptron. Here we are going to call it like a genome. So it is like a combination of several things. When it comes to the genome, it is going to be a combination of both the state, where it is, and what is the current value and where it has to go next. That is how every node can be visualized here. And mainly the objective here is actually to go for an training the neural network in such a way its performance is going to improve a lot, and it's going to learn over a period of time. That evolution has to happen. That's very important. So the neural network keeps on evolving in the sense the number of hidden layers can increase, okay, almost like this, your deep neural network. So the model will take a call, your agent, okay, whatever you're building, that will take a call like how many hidden layers can be added so that it can get a better output. That happens. And yes, so when it comes to the genetic algorithm, what is that concept taken from biological genetic algorithm is how to build upon that hidden layer. Either it will go with crossover or it will go to mutation. These two concepts are very simple. One is based on the previous states, considering that as a parental model, we take the best out of it, try to create the next trait, or we are going to take only few strides of it and we are going to come up with the new trait. So these concepts all were taken up from the genetic algorithm in order to build a neural network and to develop, to grow the neural network over there. Yes, so this was one of the example which we had analyzed. Like we have several circles. Finally, we want to come out. Okay, we are giving certain constraint like a circle of a particular color and size has to be produced finally. So out of several this thing, finally, when we keep on training the model and stuff, we will reach out in almost all the circles being of the same size, whatever we expect with the same color for say yellow here. Yes, so this was the next project what we have carried out, how to have like a car, almost an evolving AI car. It's like a sort of car controller wherein that object can navigate the path appropriately. So basically, we want to monitor, and it shouldn't hit the boundary, and it has to navigate appropriately the path. This is something what we try to develop. So what was more important over here is, as we have sensors in the real car now, we had to develop some sensors, okay, for that particular agent. So the agent here is nothing but the car. So it is going to learn that path. If you can see this video over here, based on the boundary condition, right? Those sensors, it's going to predict what in that path, which all will be the boundary condition, so that it sets a boundary and the latitude and longitude, the distance, everything was set so that appropriately it goes in the center path, it doesn't hit the boundary. And the moment it sees the obstacle also, it was updated in the policies again. So how it has to handle the obstacle, whether it is a once it hits the obstacle, what is the reward, all that was updated. So this is something, again here I've given up the code, like just displayed it, how we define a car class, how we initiate the GUI over here, and the sensor function, how it was set, and how collision detection was done. So basically, if you see, collision detection was either with respect to the boundary or with respect to the object. You can see the very basic trigonometric and mathematical stuff over here, just to predict the distance, okay, the latitude and longitude and the angle perfectly to take it in that particular track. So in every step, this calculation was done based on certain threshold value. Easily, it was able to go in the specific path within the boundary. And yes, genome evaluation, how it was done again. So when we call the feed-forward network, right, once we call it using the genome parameter, it was able to evolve the neural network internally. How it developed, everything has been explained here. And yeah, so as I told, initially what happened was there were several misses, like typically it was moving towards a boundary or it was going out of track totally, several objects, every time when that car object was getting created, that agent, it was totally going out of track over here. So this initial training was, as we all know, more number of training has to happen for it to literally go around the path and come up. So here if you see, almost like initial training everywhere, if you see, it was several losses happening throughout. So here, the moment after appropriate training has happened, in the final training, we got very good result comparatively. So finally, if you see that agent, perfectly it went to the track and it was reaching the point. So this completely, it was developed using the NEAT algorithm. Yeah, we also work with trying on different tracks also. How well, if suppose a track is going to change in between. So whether perfectly it took the other track, sorry, whether it took the other track over here and whether the result was successful. So that also we had worked on it. Okay, and the last one, the last algorithm is proximal policy optimization. So this is again one of the best algorithm which is currently being used in several reinforcement approaches. So here what we try to do is concentrate more on the policy gradient method. So basically gradient, what it does is it is going to give us an idea about the state space based on whether the when a particular state is being chosen, what is the action? That state action pair, whether it is giving us a positive reward or a negative reward, according to that, several changes was made. So basically, it follows a gradient approach over here. And I've just added few things. Very important thing is a mapping from one state to another, how the learning happens and how it is being carried out. So to put in a nutshell, based on the neural network's performance, the state policy, that policy or the state space, how it is getting updated properly, how well that update is happening so that the learning happens better and the model gives a better result. So yes, and so many parameters are used. You can just have a glance. I'll just share the material as I told in the very beginning. You can have a glance about several parameters which can be used when we're trying to implement this algorithm, but we have selected few parameters out of it. So to start with, these were the policy parameters we have used. And yes, the initial code again, okay, how we develop the code step by step. And here the game, what we tried to develop was trying to mimic a Super Mario game. So how that Mario, like we can train it so that whether it jumps across a pillar. So it so happened in the beginning when we applied it, right? All the explanations I've added, but still, okay. So it so happened initially when we trained it with initial level, if you can see, truly speaking, when we kick-started, it took almost 48 hours for it to get trained. It was literally not able to move that pillar. That never happened. We waited and waited and waited and we checked. It never happened. Then we had to do certain changes at the back end. And after changing the parametric value to some extent, if you can see over a period of time, this never happened. Even after, if you can, roughly you can see the time also. So then once we increase the epochs and, the model worked out very well. So here you can see, so slow and steadily it started moving. So how many ever pillars we had, but again there is a slight twist over here. We didn't develop the complete game and also it wasn't taking those reward points. If you see in between, it was losing those reward points, but to some extent we were successful. So once a pillar size started increasing, again it got stuck. So this approach took a lot of time with respect to training as well as getting the results. So reaching that optimal was very difficult with this approach. Might be more training and time was needed. So out of all, we felt the genome approach gave us a good result at a very short span and a more optimal result also. Is okay. So is done.
Thank you.
Thank you.
Thank you very
So
much.
due to time constraint, I had to stop over. Sorry, sir. Just a second. So these are all the students who had worked along with me, my team, for this complete project and the session. Thank you. Sorry, sir. Yeah.
Very welcome. Thank you very much for the very good presentation. And actually, the reinforcement learning is very valuable. I think in the life also can be very valuable, especially in the car collision, because they are partly applying it to prevent the accidents or to stay the car in the road. If they go out of the road, then the car can have accident and some problem. So there's this very, very good application, I think, in the future if it is developed. But this is very, very, very good field. I think it will make the life of people, maybe will save the life of people if they improve it. If you have any question, you can ask the doctor. Show me. If you, it's very, no question. I think no, maybe there is one chat from chat. Okay, they say thank you. No questions. If you have any question, you can write in the chat or you can ask directly. Open your sound. We don't have no question. So thank you very much for the nice presentation.
Thank you, sir. Yeah,
And
they can also reach out to me over the mail. Sorry, they can also reach out to me over mail. I will share my mail ID over chat.
Okay, thank you very much. So we will have the next presentation. The next presentation is the learning process of reinforcement learning. So we have already done, and the next one is reinforcement learning. So the problems and solutions. Professor Dr. Pankaj will present this topic. Can you share your screen, Doctor? Thank you very much.
Yes, sir. My screen is visible, sir?
Yeah, I can see. So I want to give some information about doctor. Sorry, Dr. Pankaj. Sorry if I pronounce your name wrongly because I'm not very familiar with Indian
Yes,
names.
Dr.
I'm sorry
Pankaj
again.
Dadheech.
Sorry. So he is the professor and deputy head Department of Computer Science and Engineering, Swami Keshwant Institute of Technology Management, and Gramothan, Jaipur. So he has expertise in Internet of Things and big data analytics, cloud computing, information system security, data mining. So very wide range of the application of like grid computing, software design. He has lots of have fields, different fields like artificial intelligence and fuzzy system. So the screen is yours, doctor. You can present.
Yes, sir. So good afternoon, all of you.
Good afternoon.
So as ma'am already discussed about machine learning, supervised learning, unsupervised learning, reinforcement learning. So just I am giving brief. So machine learning involves showing a large volume of data to machine so that it can learn and make predictions, find patterns or classify data. So generally the three machine learning types are supervised, unsupervised and reinforcement learning. So in supervised learning, it is a subcategory of machine learning and artificial intelligence. So it is defined by its use of labeled data set to train algorithms that to classify data or predict outcomes accurately. While in unsupervised learning, it uses machine learning algorithms to analyze and cluster unlabeled data sets. So these algorithms discover hidden patterns or data groupings without the need of human intervention. And then reinforcement learning, it is a machine learning training method based on rewarding desired behaviors and punishing undesired ones. So in general, a reinforcement learning agent, the entity being trained is able to perceive and interpret its environment, take actions and learn through trial and error. So it is more general than supervised and super learning and learn from interaction with respect to environment to achieve the goal. So today we will discuss some examples defining and reinforcement learning problem with Markov decision processes, and for solving the reinforcement learning problem, the dynamic programming, Monte Carlo method, and temporal distance learning should be used. So you can see the reinforcement learning is an area of machine learning concerned with how software agents ought to take actions in an environment so as to maximize some notion of cumulative reward. So due to its generality, the field is studied in many other disciplines like such as game theory, control theory, operations research, information theory, simulation-based optimization, multi-agent systems, swarm intelligence, statistics, and genetic algorithm. So you can see the robot in a room, how it performs the actions. Robot do will up, down, left, right. So move up 80%, 10% move left, 10% move right. So the reward, suppose +1 at 4-3 position and -1 at 4-2. So the reward is minus 0.04 for each step. Then resource allocation in data centers. So the load balancer where applications are there. So the hybrid reinforcement learning approach to autonomic resource allocation. Now, this is the robot in the room, how it moves. So the various states, actions, rewards. So what is the purpose? Why we are doing and what is the solution? So the solution we determine that the maximum output will be there, maximum value we can get. So only if actions deterministic, not in the case of actions are statistical. So solution is so the possibility or mapping from each state to an action. So the optimal policy, reward for each state, and then the reward for each step is minus 0.1. The various values, the reward for each step minus 0.04, minus 0.01. So in reinforcement learning, the environment is typically represented as Markov decision process, and many reinforcement learning algorithms use dynamic programming techniques. So reinforcement learning algorithms do not assume knowledge of an exact mathematical model of the this Markov decision process, and when used when exact models are infeasible. So the reinforcement learning algorithms are used in autonomous vectors or in learning to play games against a human opponent or these. So Markov decision process, it refers to a stochastic decision making process that uses a mathematical framework to model the decision making of a dynamic system. So it is used in scenario when the results are either random or controlled by a decision maker, which makes sequential decisions over time. So they already discussed the set of states, the set of actions, initial states, how the policy mapping from S to A, so the deterministic versus stochastics. So the reinforcement learning, where the transactions and rewards usually not available, or how to change the policy based on experience, how to explore the environment. So the computing return from rewards, so it is hypothetic or versus continuing tasks. So the game over after n steps or optimal policy depends on an harder to analyze or additive rewards, so that we can add up the various rewards, the infinite value for continuing tasks, or discounted rewards where value bounded if rewards bounded. So then value functions, the state value function where it is expected return when starting is as or following by. So the various states, the various actions are there, actors are there, the rewards are there, and the next state which is having very large value or the expected value. So the expected return when starting in S is performing alpha and following pi. So it is the useful for finding the optimal policy. So it can estimate from experience and pick the best action using Q. So the optimal value functions where a set of optimal policies are defined, and V as to pi defines the partial ordering on policies, and they share the same optimal value function. And the Bell-Mel optimally equation is given by this formula, where the system of n non-linear equations and solve for these each to extract the optimal policy. So then how the reinforcement learning problem is solved by dynamic programming, Monte Carlo method, and temporal distance learning. So in dynamic programming, it is defined as a computer programming technique where an algorithmic problem is first broken down into sub-problems, and the results are saved, and then the sub-problems are optimized to find the overall solution. So which usually has to do with finding the maximum and minimum range of the algorithmic query. So the two main components where the policy equation compute v pi vs to pi from pi, and policy improvement. So the policy evolution and policy improvement. So you can see the policy evolution where Bellman equation define a system of equations and could solve, but will use iterative version. So start with an arbitrary value function and iterate until vk converges. And then policy improvement by given by this formula. So the policy iteration where two nested operations too slow, and it is don't need to converge to vs to pi k, so just move towards it. Then value iteration where use Bellman optimality equation as an update, and it converges to that. So using dynamic programming need to complete model of the environment and rewards. So the robot in a room, we see the state space, action space, and transition model. So how can we use this dynamic programming to solve this robot in a room and various backgammon or helicopter, or how it will be used for other applications. So there are various state representation, the Monte Carlo method. So the Monte Carlo simulation is a mathematical technique that predicts possible outcomes of an uncertain event, and the computer programs use this method to analyze past data and predict a range of future outcomes based on a choice of action. And The Monte Carlo policy evolution where want to estimate and first visit Monte Carlo. So this is how average returns following the first visit to state as. So these are the various cases. So we used to buy not enough for policy improvement, need exact model of environment. So the estimate is Q is to pi SA by this formula, and the Monte Carlo control were update after each episode, and the non-satisfactory environment. So the problem is a greedy won't explore all actions. So maintaining exploration, the deterministic greedy policy won't explore all actions. So don't know anything about the environment at the beginning and need to try all actions to find the optimal one. So it maintain exploration where use soft policies instead of these pi essays greater than 0 for all states and actions. Then with probability 1 perform the optimal greedy action, with probability psi perform a random action, will keep exploring the environment and slowly move it towards the greedy ones. So you can see this simulated expression where various dynamic programming is used, and we use mainly the summary. Don't need model of environment. So we are averaging of sample returns on only of episodic tasks, and then concatenate on important states, or need to maintain exploration use of policies. So how this problem is solved. So the temporal difference learning refers to a class of model-free reinforcement learning methods which can learn by bootstrapping from the current estimate of the value function. So you can see the observe the following 8 episode Monte Carlo versus temporal difference. So it is the various 8 episodes are there, and the VA is 0, so converges to value that minimize their own training data. So you can see in this graph it converges to Monte Carlo estimate of the Markov process 3:4. Then SARSA, it is the state action reward state action. It is an algorithm for learning a Markov decision process policy used in the reinforcement learning area of machine learning. So you can see this is proposed by Rumeri and Niranjan, and that it is done with the name of modified connection with Q learning. So it is the alternate name of SARSA proposed by Dick Sutton. It is modified connection is Q learning. So it is start with a random policy and iterative improve or conversion to optimal. So the SARSA algorithm is a slight variation of the popular Q learning, where for a learning agent in a reinforcement learning algorithm, its policy can be of the two types: on policy and off policy. So you can see on policy in this, the state, the learning agent learns the value function according to the current action derived from the policy currently being used, and off policy, the learning agent learns the value function according to the action derived from another policy. So Q learning technique is an off policy technique and uses the greedy approach to learn the Q value, and SARSA technique, on the other hand, is the own policy and uses the action performed by the current value. So these are the various state representations and function representations, and the designing rewards where we can use, like in chess game, the good +1 for winning, -1 for losing, bad 0.25 for taking opponent pieces, or high reward even when used. So these are the various designing rewards. So we have covered these reinforcement learning where we use and need to make decisions in uncertain environment, and the rewarding desired behaviors and punishing undesired ones. So the in general we can see the reinforcement learning agent for the entity being trained is able to perceive and interpret environment, take actions, and learn through trial and error. Then solution methods through dynamic programming, we can see this is used when an algorithmic problem is first broken down into sub-problems, and the results are shared, and then the sub-problems are optimized to find the overall solution. which usually has to do with finding the maximum and minimum range of the algorithmic query. Then Monte Carlo, in which it predicts possible outcomes of an uncertain event, and computer programs use this method to analyze past data and predict a range of future outcomes based on a choice of action. So these are the various algorithms and the solutions we are used. Thank you. This is all from my side.
Thank you, Dr. Pankaj. It's very nice presentation. Anyone, do you have any questions? You can ask directly if you want to learn something, if it is interesting for you, or if you have any questions. Yes? You can ask directly. You can introduce yourself and ask the question directly. Any questions? I think somebody want to ask a question. No questions? If no question, we will move to the next presentation, the application of reinforcement learning. The presentation will be presented by Dr. Neha Janu. So the Neha Janu, can you hear me?
Yes, sir. Good afternoon.
Good afternoon. There is one message. I check it first. Okay, thank you. Thank you, Dr. Pankaj. Okay. So, Dr. Neha Janu is Associate Professor, Department of Computer Science and Engineering Manipal University in Jaipur. So she teach the classes is machine learning, data structure algorithms, and design algorithms, analyzes this kind, and also in grid computing software. So she has published some articles. She has a patent in intelligent stock trading using machine learning and artificial intelligence based. And another patent in Internet of Things sensor-based system for child monitoring and method thereof. So she has a very good CV and two interesting, very beneficial patent. So Dr. Neha, the screen is yours. Can you share your screen?
Yes, sir. Thank you so much for introduction. Just let me share my screen, please. Is it visible?
Yeah, we can see. You can start.
Just wait for a second. Good afternoon, everyone. First of all, I would like to thanks to the organizing team for this opportunity. And in this session, we will be discussing about the various applications of the reinforcement learning. As professors has already discussed that reinforcement learning is the subfield of the machine learning, and machine learning is itself the subfield of artificial intelligence. There are different types of the learning in AI, like supervised learning, unsupervised learning, and reinforcement learning. Supervised learning we can compare with our childhood days. Every time there is someone to guide us, we can compare those days. And in unsupervised learning, we can say that it is our young years. Through new and unknown challenges, we are every time we are learning something ourselves. And if we talk about the reinforcement learning, it can be compared with the old age. We learn by seeing others reactions, how they are reacting and how they are getting from those reactions. If we are talking about AI, means how to make machine intelligent that they can learn themselves. And whenever we talk about reinforcement learning, taking suitable action to maximize reward in a particular situation. It is completely dependent on reward and policy. In reinforcement learning, agents are trained on reward and punishment mechanism. Agents perform actions in a particular environment. For every correct decision, the agent is rewarded and punished for their every wrong decisions. So for sure, every time the agents tries to maximize the right decisions and minimize the wrong decision. This is always happens in reinforcement learning. We can say that reinforcement learning is the closest to human thinking. Just like we humans learn from the dynamic environment where we are living, and our actions decides whether we are rewarded or punished. Same thing is happening in reinforcement learning also. Agents whose primary goal is to maximize the reward, and we can say that it tries to, every time it tries to take the right decision. We want the AI agents to be as intelligent as human beings. So for this purpose, reinforcement learning are the base of all the solutions, from self-driving cars to surgeons being replaced by the medical AI boards. In these days, reinforcement learning has become the main driver of emerging technologies. We can see everywhere we are talking about some techniques about the reinforcement learning. There are various applications of reinforcement learning. It is used in robot navigation. It can be used for adaptive controls such as a factory processes, admission control in telecommunications. Reinforcement learning can be used in game playing also. Reinforcement learning can be used for optimizing the chemical reactions. Nowadays, reinforcement learning is used for business strategy planning also. In various automobile manufacturing companies, the robots use deep reinforcement learning to pick goods and put them into some containers. Reinforcement learning is also currently used in the finance sector for evaluating trading strategies also. From all about these applications, we can say that reinforcement learning is one of the most interesting and useful part of machine learning. In reinforcement learning, the agent explores the environment by exploring it without any human intervention. It is the main learning algorithm that is used in AI, but there are some cases where it should not be used. We can say if we have efficient data for solving any particular problem, then we can use only the machine learning algorithm. In that case, if we are using reinforcement learning, it will increase the time for solving that particular problem. So there are some situations where reinforcement learning cannot be used. Among all these applications, some of the applications we will discuss in details. If we talk about the self-driving cars and think that how we can assure that self-driving car has already learned all possible scenarios and safety measures for every situations. Yes, of course, for ensuring this, every time the answer is reinforcement learning. As we know previously in the market, the Tesla autopilot system still requires humans to perform some tasks, such as switching lanes to overtake a slow moving car. We know that reinforcement learning models are trained in a dynamic environment. They learn all the policies from its own experience, following the principles of minimizing the disturbance to traffic. Self-driving cars have many aspects like driving zones, traffic handling, maintaining the speed limits, avoiding collisions are the significant factors to consider depending on which it make it optimal decision. There are many simulation environments for testing and reinforcement learning models for autonomous vehicles technologies, like deep environment that combines the powers of reinforcement learning with deep learning and computer vision to build algorithms for autonomous driving. Deep traffic simulates the autonomous vehicles such as drones, cars, and more. Calra is also another excellent alternative that has been developed to support the development, training, and validation for automation of driving systems. These dynamic environments are used by reinforcement learning agents to optimize the route. The agents learn motion planning, route changing, decision and position of parking and speed control. All of these things, these are learned by the reinforcement learning for autonomous cars. Our next application is data center schooling. We know that we are living today in the world where world's most challenging physical problems such as energy consumption can be tackled with the help of the artificial intelligence. Today, where the entire world is talking about virtualization and cloud computing, cloud-based applications, due to this large-scale commercial and industrial system like data centers have a large energy consumption to keep the server running. For cloud-based application, availability of data is most critical thing. For ensuring this high data availability, server needs to keep running all the time because the large organization cannot bear the loss due to unavailability of data. Here we can see a case study of Google. In 2016, Google reported that reinforcement learning has reduced the energy bill of their data centers by 40%. Here, simplified version of the problem, there is a data center having various racks of servers and workers. We know continuous running of servers produces heat, and this makes workers to feel uncomfortable with the high temperature. But Google wanted to but for controlling this high temperature, we need we need to establish some air conditioners that can be installed on those server rooms for maintaining this temperature. But Google wanted to minimize the energy bills for these air conditioning system. In this problem, the state may consist of information of indoor temperature can be there, outdoor temperature, and other situations like outdoor humidity and many others. Here action is what type of action can be there, the cooling system, heating system, set points and thermostat. We can see that as an example, if the indoor temperature above air condition system will cool the room. But if the set point is between the cooling and heating system, the the air conditioning system does not do anything. But if the cooling system is below the temperature, then it will start cooling the environment. So that is and it was so good that in 2018 a review article reported that Google has now given complete control of the air conditioning system of their several data centers to deep in reinforcement learning. But yes, of course, by saving it makes the sense, because it is saving more money for that organization. So everything is handled by the reinforcement learning. And this is not only the single industry which is taking which is using reinforcement learning application. There are various industries which are using reinforcement learning for their environment. Next application is traffic light control. We know that with the increase in the number of cars per household, traffic congestion has become a huge problem. Specifically in metropolitan areas, people spend too much time on road. Traffic congestion cost is increasing. Therefore, people are making lot of efforts for optimizing the traffic light. So how to control these traffic light is most challenging task. In general, there are only two types of the traffic signal control systems used. First one is fixed time signal and second is activated signal. For adaptive traffic signal control, reinforcement learning is a trending data driven approach. These models are trained with the objective of learning a policy using a value function that optimally controls the traffic lights based on the dynamic behavior of the traffic. The decision making needs to be dynamically depending upon the arrival rate of the traffic from different directions as traffic varies at different times of the day. Next application is healthcare. In healthcare department, healthcare is an important part of our lives, and through dynamic treatment regimes, doctors can discover the treatment type, appropriate doses of drugs, and the timings of taking these doses. We know that choosing treatment is very hard. It is even more challenging when the patient has become on medication for the long years and no improvement have been seen. Recent research shows that a patient suffering from chronic disease tries different medicines before giving up. We must find the right treatment and map them to the right person. The healthcare sector has always been an early adopter and a significant beneficiary of technology advancement. This industry has been a significant towards reinforcement learning in the past few years, especially in implementing dynamic treatment regimes that are called DTRs for patients suffering from the long-term illness. It has also found its application in automated medicines, diagnosis, health resource scheduling, drug discovery and development, and health management. When a series of decisions need to be taken, then reinforcement learning is only the solution that comes into the picture at that time. Next application of the reinforcement in marketing. Reinforcement learning is used in various marketing spheres to develop techniques that maximize customer growth and strive for a balance between long-term and short-term rewards. We can see the various scenarios where real-time via reinforcement learning is used in the marketing space. First one is customized recommendation for customers. Personalized product suggestion give customers what they want. The reinforcement learning bot is trained to handle situations where challenging barriers like reputation, limited customer data, and customer involving mindset are dealt with. It dynamically learns the customer's requirement and analyze the behavior to serve high quality recommendations. This increases the ROI and profit margins for the company. Creating the most beneficial content for advertisement, coming up with the best marketing pitch that attacks large amount audience is challenging. Models based on Q1 learning that already discussed with the professor are trained on the reward basis and developed an inherent knowledge of positive actions and the desired results. The reinforcement learning model will find the advertisement that the users are more likely to click on, thus increasing the customer footprints. Identifying interest area of customers with stores, CCTV to deliver better advertisements and offers. Next application is inventory management. The inventory management is in big companies and warehouses has become automated with the invention in the field of computer vision to track stock in real time. Deep reinforcement learning agents can locate empty containers and ensure that restocking is fully optimized with the help of reinforcement learning. Next, we can discuss the applications of reinforcement learning in robotics. Also, robotics operate in a highly dynamic and ever-changing environment, making it impossible to predict what will happen next. Reinforcement learning provides a considerable advantage in these scenarios to make the robots robust enough and help acquire complex behavior in different scenarios. It aims to remove the need for time-consuming and tedious checks and replace them with computer vision system, ensuring higher level of quality control on the production assembly line. Next application we can discuss, it is having in gaming also. Reinforcement learning has taken over the traditional methods of creating video games as compared to traditional video games where we need to have a complex behavior tree to craft the logic of game. Training a reinforcement learning model is much simpler. Here the agent is set to learn by itself in the simulated game environment by performing the necessary sequence of actions to achieve the desired behavior. In this reinforcement learning, the agent should be trained for all the aspects of game like pathfinding, defense, attack, and creating situation-based strategies to make the game interesting for the opponent. Depending upon the intelligence the bot has obtained, level of the game is set. Google DeepMind is the live example of the game optimization. We have seen AlphaGo and RL trained agent beat the strongest Go player in the history, scoring the goal that was considered impossible at the time. It is known to be very challenging game for artificial intelligence. With these applications, there are various applications where fields where we can use reinforcement learning. They are not limited to only these applications. Researchers are still working that we can use in every field this reinforcement learning. This was all about the application, some of the applications of the reinforcement learning.
Thank you. Thank you very much, Dr. Neha. This Yes, it's very, very interesting. I think if they develop this reinforcement learning, because it has very wide areas, especially in the saving energy and the preventing the wrong movements like collision in the cars or improving the games. So, and the most important part, learning by itself. And when there's they don't have enough data, this kind of machine learning technique is very beneficial. But as I told you, still it's in developing stage, I think. Dr. Neha, Oda, or
Yes, sir.
it's still in
Yeah,
developing
yeah,
stage.
yeah, yes, sir.
I think that this algorithm is not very developed, or
Yes, sir. Yeah, they are in a developing stage still, na? Or there are various fields we can explore these algorithms. They, in this short duration, we cannot learn all these applications. Na? We can simply discuss this introduction of these applications. If we
yeah,
will take one by one, then it will take long time, because
yeah,
researchers have done many work in all particular single applications.
yeah.
Yeah.
Yeah, then they try to develop the algorithms which is better than the all the other ones, and if they are beneficial, probably they will be selected. But logic is very, I mean, the logic of the maximization of reward and is very logical, I think. But it
Yeah,
is the programming side, I think, is very important, and
yeah,
the visualizing side is very important, and how they connect this to the real life. So we need to see the application. I think in the gaming it's easy to see this kind of things, but for the others still,
still in
maybe,
developing stage. Yes,
yeah,
gaming
because it's
is
very, if they can prevent the collisions like the cars or accidents, or
yeah,
like
that
saving the energy in the room, if they can save more energy in the room, because they you can combine many things together. So we will see, but it's very interesting topic from my side. I have learned a lot of things from the reinforcement learning. So if you have any question, you can ask the Dr. Neha or other presenters. If you have any questions, if you want to, I have shared the attendance form. You can fill it, and you can get the certificate. It's free. So I shared in the message. So, any questions to Dr. Neha? No, I think no questions. So the Dr. Krishna is here. The Dr.
Yeah,
Krishna, we
I'm
have
here,
finished
Dr.
the,
Imran. Very
yeah, we
nice,
have
very nice.
finished.
Thank
Yeah,
you
yeah,
for
very,
coordinating.
yeah.
I think we can close the session.
Yeah, thank you very much, Dr.
Thank you
Krishna,
all.
who
Thank
is
you
the
all.
main organizer of this presentation, and he will put this video on YouTube. So probably more people will watch it, and when they have time, or when they search in the YouTube or on the other digital platform, they can get this video. So thank you very much for the presenters and the participants. I hope you enjoy it. Thank you very much again.
Thank you all. Bye. Bye.